Good day, everybody. Thanks for joining this section. My name is Huang and I'm from Mobile Perception Lab at Shanghai Tech University. In this paper, we introduce a method using B-spline for visual SLAM on non-holonomic ground vehicles. We show that a significant increase in robustness can be achieved by taking non-holonomic kinematic constraint on the vehicle motion into account. Please note that our lab has 3 papers at ICRA 21, which are very related topics. For further information, you are invited to visit our webpage. Bound adjustment plays an essential role in most state-of-the-art feature-based visual SLAM, and it is typically used for the final refinement stage to approximate initial estimates and remove the scale drift in incremental reconstructions. It jointly optimizes the camera poses and 3D position of landmarks by minimizing the reprojection errors. Such objective functions are generally optimized using nonlinear least squares algorithms and can be efficiently solved by implementing iterative methods. These methods depend on sufficiently good initialization obtained from front-end solvers. However, there are many complicated and challenging scenarios in practical application, which makes the failure of front-end solvers very likely. We notice that the trajectory in visual SLAM frameworks is commonly represented by a discrete set of camera poses. The discrete representation is too general and doesn't respect the kinematic motion constraint of ground vehicles. To develop robust SLAM solution for self-driving vehicles, we consider taking a more restrictive but exact kinematic constraint on the ground vehicle motion into account, which is the ACMA motion model. Here we start by reviewing the basic idea of continuous time parametrization, which plays an important role in motion estimation when dealing with smooth trajectories. We use the efficient and smooth B-spline parametrization as already illustrated by Fergal before. According to the definition, a B-spline curve is defined as a linear combination of control points and B-spline basis functions. The basic form of a p-degree B-spline curve is given as follows, where u is the continuous time parameters, p underscore I at n plus 1 control points, and n underscore ip are the p-degree B-spline basis functions. We initialize B-splines based on discrete set of camera poses. As we mentioned before, the ground vehicle with a non-steering two-wheel axis is commonly undergoes non-holonomic motion. This kinematic constraint is reflected in the ACMA steering model, and the instantaneous heading of the vehicle is parallel to its velocity, which gives the RV constraint. Also, this kinematic constraint can be approximated by a circular arc, and the heading remains tangential to its arc, which gives the RT constraint. This is a conventional bound adjustment, which minimizing the reprojection error between poses and landmarks. The figure is a graphical model of objective. RQ is a rotation matrix constructed from quaternion representation Q. T underscore Bj and Q underscore Bj are optimized pose parameters. X underscore I are landmarks in homogeneous representation, and M underscore Ij is the observation of landmark I in frame J. Rho represents a loss function, such as Hilbert loss, to mitigate the influence of outliers. T underscore SB represents the extrinsic parameters. Fp is a projection function. We now proceed to our work, the optimization of non-holonomic trajectory. We first introduce the aforementioned RT constraint. The constraint can be added as a pairwise soft regularization constraint into the formulation, which is a traditional way of adding non-holonomic constraint. W underscore R is a scalar weight for the RT constraints, and these two denote the relative rotation and translation between subsequent wheels. Such an objective still optimizes a discrete set of poses and regularizes it against a piecewise circular arc model. Hence, we extend it to a continuous time model. We formulate the continuous time model by replacing the previous RT constraint with a soft, regularizing RV constraint, which using a 3D spline approximated from the position. As shown in the equation, P is a set of control points. C1 denotes the fitted spline. T underscore J is the timestamp at J's frame. Eta denotes the normalization of the first-order derivative of the spline. In our next formulation, the spline is used directly to represent the poses. Only the kinematic RV constraint remains as a side constraint. Our final objective consists of directly using the derivative of the continuous position to express part of the vehicle orientation. As shown in the figure, we could formulate the poses in 4 dimensions, 3 for translation, and the first derivative plus a roll angle as rotation. We test our algorithm on both synthetic and real data. The main purpose of our experiments is to demonstrate the ability of our methods to handle degraded visual conditions. We analyze the influence of the connectivity of the graph by varying the number of landmarks and the number of observations, and also the commonly analyzed influence of noise on the image measurements. Previous experiments used the original ground truth trajectory from Kitty VO5 dataset. Here we use sparsely sampled artificial trajectories. As can be seen from all the results, our proposed method has significantly improvement under such degraded visual conditions, especially when the including spline approximation. In real data experiments, we use the Kitty benchmark datasets and carefully add noises artificially to simulate degraded visual conditions. Blue dashed lines represent the original result, as expected, which is generally improved upon after optimization. CBA carefully has the worst performance. Our robust BA methods provide the highest accuracy. The proposed method shows significant improvements in both accuracy and robustness, especially the connectivity of the graph or the quality of the measurement degrades. Here are some qualitative results. As we can see from the experiment results, for graph with low connectivity, FSBA leads to the most stable and accurate result. For graph with better connectivity, CBA SPRV outperforms due to the unevenness of the ground surface and the accuracy of extrinsic calibration parameters. In conclusion, we introduce continuous time trajectory parametrization for exact modeling of non-holonomic ground vehicle trajectory in bound adjustment. Its additional strongly improves the accuracy and the robustness of monocular visual odometry, especially as the connectivity of the graph or the quality of the measurement degrades. Thanks for listening.